You ever train an AI model that looks like an absolute genius on paper, only to watch it completely faceplant in the real world? Well, the problem might not be your model at all, but how you're testing it. Today, we're going to pull back the curtain on a super common issue in AI that can give you a totally false sense of confidence. And then, we'll reveal the elegant solution that the pros use to get a score they can actually trust. All right, here's our game plan. First, we'll talk about something called the performance lottery. Then, we'll introduce a much better way to test our models. We'll break down exactly how it works, see the massive difference it makes with a real example, and finally, wrap up with why this is so important for building AI we can count on. So first up, the performance lottery. This is this kind of scary idea that when you go to evaluate your model, its final score can be massively influenced by just pure random luck in how you happen to split up your data. Think about it like this. Imagine you're a teacher grading a student, but instead of a big final exam, you give them one single randomly chosen pop quiz. If they happen to get the easy quiz, they look like a genius. But if they get the one with all the tricky questions, they look like they've learned nothing. This is exactly what can happen when we test our AI. You know how it works, right? You take your data, you split it into a training set and a validation set. The model learns on one, you test it on the other. But here's the catch. A single one-time split can create what we call evaluation noise. You might have accidentally put all the easy examples in the test set, making your model look great, or all the hard ones, making it look terrible. Either way, that score isn't the real story. And this really shows you the scale of the problem. With just one random data split, it's pretty normal for performance scores to swing wildly. We're talking 5 to 10%. That's a huge margin of error. But with a method like k-fold cross-validation, or CV, that variance just collapses, stabilizing to a tiny deviation of maybe 1 or 2%. That's the difference between a wild guess and a reliable measurement. Okay, so this brings us to the solution. To get out of this performance lottery, we need a much more reliable test. And that test, my friends, is k-fold cross-validation. So let's go back to our student. Instead of one random pop quiz, what if we gave them, say, 5 different tests that cover all the material, and then just averaged the scores? That average score would be a much more accurate picture of what they actually know. That, in a nutshell, is the genius idea behind k-fold cross-validation.
So if we want to get formal about it, k-fold CV is a resampling procedure. It's a clever way to get a more trustworthy performance score by running a bunch of mini experiments on your data and averaging out the results. It's designed to squeeze the most reliable information out of the data you have.
Okay, so how does this magic actually work under the hood? Let's break down the nuts and bolts of this awesome technique. It's a really simple but brilliant process. First, you take your data and you just chop it up into a number of equal parts. We call these folds. Let's say we use 5. Then for round 1, you hold out the first fold for testing, and you train your model on the other 4. You get a score. Great. Now for round 2, you hold out the second fold and train on all the others. You get another score. You keep doing this, rotating which fold is the test set until every single one has had a turn. And for the grand finale, you just average those 5 scores together. That's it. That's your final, much more reliable performance estimate.
Now, k-fold is already a powerful idea, but we can actually level it up to make it even more robust. See, there are different flavors of it, and a really crucial one that you'll see data scientists use all the time is called stratified k-fold.
So what on earth does stratified mean? Well, it's just a way to make sure that every single one of your folds is a perfect little miniature of the full data set. So if your overall data is, say, 70% apples and 30% oranges, stratification guarantees that every single fold will also have that same 70-30 split. This is absolutely essential when you're working with imbalanced data, so you don't accidentally get a fold that has like 0 oranges in it.
Okay, that's enough theory. Let's see this thing in action with a real experiment. We're going to put the noisy single split right up against the stable cross-validation score and see what happens.
So here's the setup. We're using the classic iris flower dataset with a k nearest neighbors model. Our mission is to find the best setting for a key parameter, k, which is just the number of neighbors the model looks at. And we're going to do this twice. Once the old-fashioned way with a single validation split, and once using a 5-fold cross-validation. And boom, just look at those results. The difference is night and day. The score from the single split is jumping all over the place, from 94% accuracy all the way to a perfect 100%. It's incredibly noisy, completely unreliable. But then look at the 5-fold CV score. It's rock solid, hovering right around 97.3% with only about a 1% wiggle. Now that is stable, trustworthy, and gives us a clear signal. This stability is everything because it's what allows you to make confident decisions. When you actually plot these scores out, the cross-validation result gives you a nice, smooth curve, making it super easy to see which model setting is truly the best one. The single split, on the other hand, is so erratic and jagged, trying to pick the best setting from that is pretty much just a shot in the dark. So let's bring it all home and talk about why the seemingly small technical detail is so incredibly important for building AI systems that you can actually trust. To sum it all up, K-fold CV is all about replacing luck with reliability. By averaging across multiple splits, we get a stable score that lets us confidently choose the best model for the job. And as a really nice bonus, it's incredibly data efficient. It makes sure that every single piece of your precious data gets used for both training and testing at some point. At the end of the day, it really just comes down to this. Using cross-validation gives you a performance score that you can actually hang your hat on. And having a trustworthy measure of performance, well, that's the absolute foundation for building any reliable AI system, whether it's for medical diagnosis or self-driving cars. So the next time you see some big headline-grabbing accuracy score for a new AI model, I want you to ask yourself this question. Was that score from a single pop quiz, or was it the average of a comprehensive final exam? Because your model's score is just a number, and now you